have a pointer here?
There was a long yesterday. We had that
Yeah,
over
that's
there. It's and another one on the other side actually. We have two.
All right, we can use this.
They are old-fashioned ones. So
Okay, that's fine. I think it's on, no?
No.
It's all recording.
Oh,
It says so.
sorry.
So you
Okay.
can start.
So Raja will be talking about circularity, paradoxes, and proofs.
So, good afternoon, and thanks for coming to this talk. I work in an institute which is called the Tata Institute of Fundamental Research. It's in Bombay, now called Mumbai in India. My research interests are largely in proof checking and interactive theorem proving. But today's talk is not going to be on that. There are certain other subjects also I'm interested in. I thought I would speak to you about one of them. So, and for lack of a better title, I've called it Circularity, Paradoxes and Proofs. I hope it's not totally inappropriate. I'll explain the connections. So, here is the major objective motivation for this line of research. So, it's to an observer of research and logic in foundations of mathematics or in mathematics itself. It's kind of quite clear that people try to prove theorems, they try to come up with alternate proofs of theorems, and not just that, while trying to find out alternate proofs of theorems, there is also some kind of conscious or unconscious effort to try to see whether you can prove theorems without using certain kinds of logical primitives. In the sense that you limit the kind of repertoire you have of basic constructs that you can use for doing proofs, and then consciously limit yourself to a subset of them, and then see whether your proofs go through in spite of that. Okay, so this is the kind of approach that I'm trying to do in this research. If these points look too crazy to you, most of the talk is going towards explaining this in slightly more detail. Okay, so right. So if you look at paradoxes, now I put down a whole list of them. This is not an exhaustive list. There are plenty more. It's just a representative list that I have. So if you can think of paradoxes, formulating a paradox as similar to proving a theorem, then there are a lot of analogies between these two, which I'll touch upon. So when you have a paradox, so there is an underlying formalism which has lots of things. There are things like self-reference, there is cross-reference, there are operators like negation, and then there are references to other things called semantic values. There's a whole lot of things that go into these paradoxes. And if you look at this work on paradoxes, there seems to be some kind of a theme that runs through them, which connects later day paradoxes to earlier day ones, in the sense that people have tried to do what I mentioned just now, trying to formulate those paradoxes, earlier ones, using a much less or much limited number of constructs at their disposal to be able to formulate the paradoxes. So a similar theme runs in proofs of theorems in logic. So there are similar things like circularity, self-reference, diagonalization, negation operators, a number of them that go into these theorems, and there are plenty of different proofs which either make use of them or avoid them. So here is the basic agenda of my talk. I've told you very briefly about the objectives, and I'm going to illustrate what I've told you just now using 4 different kind of examples. So I'll tell you about Russell's paradox and negation, the relation between them, and then I'll tell you about Liar's paradox and self-reference, in the sense, can we do Liar's paradox without self-reference? Is it possible at all? Is it an impossible task? Similarly, can we avoid negation while doing Cantor's theorem? This is Cantor's theorem in set theory, and similarly diagonalization in Cantor's theorem. So once we're through this list, I'll summarize and then stop. So let's look at Russell's paradox, one of the easiest ones to state today. So just to remind you, it goes like this: the set of all sets that are not members of themselves is both a member of itself and also not a member of itself. Okay. So what we are interested in focusing is there is a presence of a negation here. In order to construct the Russell set, I am not talking about this negation, I am talking about this one. Right. So the question is, can you make a Russell set, a Russell-like paradox, in a logic which doesn't allow you negation? Okay. Now this is not too crazy a question. There are things like paraconsistent logics and other things which don't allow you negation. Okay. So just throwing away negation from your formalism doesn't get you out of Russell's paradox, provided the negation is kind of essential to do this. You know, if Russell's paradox is too intimately tied with negation, then once you throw away negation, you are free from Russell's paradox also. Okay. So let's see whether what's the connection between them. Now there are more colorful ways for stating the Russell's paradox. There is the Grelling-Nelson paradox, which can be stated in terms of English adjectives. For example, so look at adjectives, and we note that there are certain adjectives which describe themselves and some which don't. So for example, English is an English word, while French is not a French word. So I don't know French. Apparently, Francais is when you say French, when you want to say French in French itself. Similarly, when I say a word is made up of several syllables, it's polysyllabic, and this itself is made up of several syllables. It's polysyllabic itself. On the other hand, the adjective monosyllabic is not monosyllabic. So next we classify all these adjectives, and we say that all those adjectives that describe themselves, let's call them autological, and the adjectives that don't describe themselves, we call them heterological. The next question we ask is heterological itself heterological? So, and it turns out that it is, if and only if it is not. So this is Grelling's paradox. So we get that it's not possible to classify all these adjectives into two neat classes like this, autological and heterological, and then so it's very easy to translate Grelling's paradox into Russell's paradox. You just identify each adjective with the set of objects to which it applies, and then the autological word is a set, one of whose elements is the set itself. So this comes back to Russell's paradox, and the question of whether heterological is heterological is the same question as determining whether the set of all sets not containing themselves, they contain themselves as an element. Okay. So the person to look at this, and one of the people to look at this in more detail was Haskell Curry. So Haskell Curry presented a whole series of paradoxes which are now called Curry's paradox. So this doesn't refer to a single paradox but a whole family of them, and he gave certain conditions about the requirements of a language in which these paradoxes can be formulated. Okay. So there are plenty of different sets of conditions. I'll just state one of them. So if I have a family of languages which contains the following, it contains some kind of an apparatus which lets it refer to and talk about its own sentences, some kind of indexicals, there's quotation marks or names or things like this sentence, and then it also has its own truth predicate. So it contains a predicate, it says true and else, yeah, and the ability to ascribe this predicate to any sentence in that language. So if you have a language which allows you these kind of things, then immediately you can construct a paradox called Curry's paradox. So a language which allows you those things are set theories which have some kind of unrestricted comprehension. So if you give me a set theory which allows unrestricted comprehension, then it's possible to prove any statement y. Y is an open statement. You can prove anything that you like starting from a definition like this. Okay. So the proof of y goes like this. We start with this definition. Here's the definition of x. I instantiate it to x, and then here is a double arrow. I go from left to right in the first instance. So that gives me step number 2, and then 2 is of the form p arrow q, use contraction, and then I have step number 3. Okay. And then you go back to the definition and then initialize it going from right to left. That gives me step number 4, and then from 3 and 4 use modus ponens. I have 5, and then from 3 and 4 once again with from 3 and 5 I have modus ponens, I have y. Okay. So here is a proof of any statement. So you can plug in whatever you want for y. Okay. The 1 is equal to 2 or whatever you like. Okay. So you can prove anything that you like, and this is Curry's paradox. So what's of what's interesting to us here is that unlike Russell's paradox, the Curry's paradox doesn't depend on what model of negation is there in the underlying language, because it's completely negation free. The Curry's paradox, the Curry's paradox is totally negation free. So like I said, there are logics which throw away negation. So in those logics, it turns out it's easy to avoid Russell's paradox, but it's a much harder task to resolve Curry's paradox in them. So it takes a lot of non-trivial work to be sure that you don't run into Curry's paradox. So all right, so that was the first example that I wanted to tell you about. So the summary of this is, it is possible to do Russell's paradox without negation, right? So let's look at the next one. Let's see Liar's paradox. So there are several formulations of Liar's paradox, like this sentence is false, I'm lying now. There are several of them. So apparently it's supposed to have appeared in the Old Testament for the first time, where one of the teachers claims about the local pagan population. He says they are all liars. One of them themselves claims to be a liar. So, and then but apparently this is much older than that. Almost 600-700 years before this, there is reference to this in Greek philosophy, where there was Euclides who wondered. He says a man says he's lying. Is what he says true or false? Okay. So now the thing that we want to focus on here is look at the Liar's paradox, and it refers the paradoxical sentence. It refers to its own truth value. Now the question we ask is it essential that this sentence should refer to its own truth value in order to construct a Liar's paradox? Okay. So, and the first answer is quite simple. You can do this. You just split one sentence into two. Okay. So I have two sentences now. The first one says the following sentence is true, and the next one says the preceding sentence is false. So neither of them refers to their own truth value. They are talking about the truth value of something else. Okay. And then it turns out that you can make this longer and longer, but still there is something which okay, let me skip that. So all right. So the next question you ask is there a way to avoid self-reference as done in this word and still construct a paradox using just a single sentence? So there comes in Quine to help us. Okay. So here is Quine's paradox. It will look totally crazy. It looks as if somebody has just made it up, but it's true. So here is Quine's paradox. So there is something within double quotes and there is something outside double quotes, and they are identical things. Okay. The same thing that's repeated within here. Okay. And if you look at this carefully, it turns out this is an algorithm for constructing another sentence. Okay. So the thing outside the quotation marks gives you some rule to apply to the stuff within the quotation marks. You do all those things and you end up with the same sentence itself. Okay. So let's denote capital Q as the phrase yields falsehood when appended to its own quotation, and then I put the Q within quotation marks. This is what I get, and then I append Q to its own quotation and I get back the sentence that I started with. This was the Quine sentence. Okay. So if you read this carefully, essentially it says that this sentence is false. Okay. So it gives you a rule for constructing some sentence and says that when you finish making that sentence using those rules, the sentence that you get is false. So the starting sentence and the ending sentence are exactly identical. Okay. So this is just the Liar's paradox. So right. Now if you look at paradox and see circularity, if you look at Liar's paradox, all of them seem to require circularity in some unavoidable way. Okay. There is either direct self-reference or there is some kind of indirect loop like self-reference, and you can make this longer and longer, but essentially there seems to be some self-reference. So the question is self-reference an essential condition for constructing logical paradoxes? Okay. And this was unanswered for a long time until Stephen Yablo came up with an answer to this, and strikingly it turns out that it is possible to construct paradoxical sentences without invoking either direct or indirect self-reference. Okay. So you have a formalism which doesn't allow you to do self-reference, either direct or indirect, and you can still build up the liar's paradox, and that is Yablo's paradox, which is some kind of a non-self-referential liar's paradox. So let me show you Yablo's paradox. This is how it goes. So I have an infinite sequence of sentences, say Si, S0, S1, S2, and so on, and all of them are identical. Okay. So sentence Si says for all values of j greater than I, Sj is false. Right. So assume I have a whole sequence of sentences. The first one says all the following sentences are false. The second one says all the following sentences are false. The third one says the same thing. The fourth one says the same thing. All sentences are identical, and I have an infinite sequence of them. Okay. Essentially, that's what this amounts to. Okay. So but what is of interest here is pick any statement, and you find that this statement, it refers to only statements which come after this in that sequence. It doesn't refer to things which come before. Okay. So now suppose Sk is true for some value of k. What does this mean? It means Sk plus 1 is false, because it asserts all the following sentences are false. So Sk plus 1 is false, and all the other subsequent statements are also false. So what does this mean? Which means that this will make Sk plus 1 also true, because everything from Sk plus 2 is indeed false now. Right? So what we have is so Sk plus 1 turns out to be true. Right? So we have a contradiction here, and so Sk is false for all k. Once you have this result, now you focus on any particular I. This means that Si is in fact true, because everything after that is false. Okay? So you get a contradiction. So essentially we have the liar's paradox once more, but what's interesting here is in this sequence every sentence refers to something only forward. There is no going back in this. Okay? So there is no, the loop is never completed. So I have an infinite sequence, and so it's something taking this to a limit. So we started with a single line liar's paradox, split it into two. It's possible to make this longer and longer, and Yablo takes it to the limit. I have an infinite number of sentences, and still can construct the liar's paradox without having to go back to any of the earlier ones. All right. So this result comes from Stephen Yablo, who showed that self-reference can indeed be done away with. And then let's look at the next result in the same series. Let's look at Cantor's theorem and negation. So the Cantor's theorem that I am talking about is the one from set theory. So it says for any set there is no function that maps its members onto all its subsets. Okay? A very simple theorem. I mean, the proof is there in all the undergraduate textbooks. So there is a standard diagonalization proof which achieves what you want. So it constructs a set along the way, and then shows that clearly this set cannot belong to the range of any function that you consider. Okay? So this is a proof by contradiction. You start by assuming that you can indeed do such a thing, and then show that there is one set which will get left over irrespective of what mapping that you start with. Okay? And look at the construction of this particular set. This seems to need the notion of negation in order to build this. Okay? Now the question is, can I do a proof of Cantor's theorem which shows me a leftover subset which doesn't use a negation operator to construct it? Okay? And that's the next thing that I show you. So here is a slightly different proof which hopefully you have not seen before. So we have the same theorem, Cantor's theorem, which talks about the cardinality of a power set being greater than the cardinality of a set. So let's go through this a bit slowly. So let X be any set, and P of X is the power set of X, and we have and we want to show that there is no one-to-one correspondence between them. Start by assuming the exact opposite. Assume that I have a function m which does this mapping. Okay? Now I need some intermediate definitions. I define something called a trace. So what is a trace? Trace is just a sequence of elements from the set X. So S0 is any arbitrary element from X, and S1 is an element of m of S0. So start with S0, find out where does this m map S0 to. So S0 will get mapped to an element of power set of x, which is a subset of x. So pick one element from that and call it S1. Okay. So I have a choice here, and then similarly find out where does S1 get mapped by m, and pick an element from m of S1, that's S2, and keep going on like this. So we will call this a trace, and so the first element of the trace is any arbitrary element of x, and all the other further elements of this trace follow this simple rule. Okay. Now forming a trace is a non-deterministic operation. I mean, you have some choice at every step. So so starting from the same first element, I get several different traces. Now I have another definition. I'll say that T of x is a simple element if all possible traces that you can construct with x, they all terminate. Okay. Now when does trace terminate? If you start with S0, then you come up to a terminating trace, provided you run up into an element which m maps to the empty set. So there is nothing else you can pick from its range. Okay. So all right. So now I have a new set which collects all such simple elements and puts them together. Okay. And the claim is this set, which is a subset of x, this cannot lie in the range of m. Okay. So this is analogous to the diagonalized set D that I showed you in the standard proof of Cantor's theorem, and the claim is this also is outside the range of any mapping which claims to be one to one. So how do we establish that? Suppose that there does indeed exist an element of x such that m maps that element to this set n, then we can see that element, the lowercase n, should also be a simple element, because if I begin any trace starting from n, then the first element I have is lowercase n, and the next element I have to pick from this set uppercase n. Okay. And we know we have the property that all elements that start with this, they end up in terminating traces. So even if I begin with this, I still have a terminating trace. Okay. So once this is true, which means I have to throw in this element also into this set, but once you do that, you no longer then you see that this is no longer a simple element, because you have non-terminating traces now. I can start with n, and then I can keep on repeating the same thing, and I have a non-terminating trace. Okay. So what have we established? That this set is out of the range of any one-to-one correspondence, supposed to be one-to-one correspondence between x and p of x. Okay. And the important thing to notice in this proof is that the construction of the set n doesn't require explicit negation. Okay. And this is different from the standard diagonalization proof. I mean, of course, you can say the same thing also holds for the usual diagonal argument, where you talk about natural numbers and reals, and there is a way of showing that the reals and natural numbers don't have a one-to-one correspondence. So you can probably say that even that proof can be thought of as one which doesn't need negation. So all right. So let's go back to the proof that I was showing you. So you can look at this as some kind of a generalization of Cantor's argument. This sequences that I made, I can generalize them slightly more from I call suppose k is greater than 0, and I consider sequences starting from t going up to sk. Then I define traces, things which are called k simple, provided there is no such sequence which has this property. So I start with t, and then the first element S1 comes from m of t, and so on, and finally t is an element of m of sk. Okay. So if this property is not valid, then I will say that t is k simple. Now you can for every value of k from 0, 1, 2, 3 and so on, you can collect all the k simple elements into corresponding sets, and you can see easily that each of these n k's are all out of the range of any one-to-one correspondence m. Okay. So I have several such sets, and Cantor's argument has the most basic case where there is n0, in the sense that I consider 0 simple sets where t is not an element of m of t. Okay. And in the other proof that I showed you, So we make use of all these nks as intermediaries before we end up with the final set n. Okay. So there is some kind of an analogy with Yablow's paradox, where starting from these sequences for larger and larger values of k, you actually end up by going to omega. Okay. So I have an infinite sequence. So and that finally gives me another set which is outside the range of the one-to-one mapping. So it's perhaps immediately not clear whether n doesn't use negation. So here is the definition of n: the set of all t an element of x such that t is a simple element. So to find out whether this is negation free, you try to rewrite this, expand this a little bit more, and so the statement that we have here is all possible traces beginning with t terminate. We have to determine whether this is negation free. So an obvious way to rewrite this would go like this: you say there is no non-terminating sequence such that this property holds. Okay. So on first look, it looks as if there is a negation here, but it turns out that I have another negating property. These two cancel out, so negation disappears from this formula. So you rewrite this in such a way. We say that for k greater than or equal to 0, an element S0 will be called simple when for every possible sequence S0, S1 up to Sk, there exists an f such that m of Sf leads up to the empty set. Okay. So that gives me a terminating trace, and this characterization is negation free. Okay. So that was the third example I showed you, and then I have a very short final example. So what about Cantor's theorem and diagonalization? Is it possible to do Cantor's theorem without diagonalization? It turns out that Cantor himself answered this question, and the very first proof that he had of this theorem did not use diagonalization. But you don't see this book, you don't see this proof in books on logic. Sometimes you see them in books on analysis. But this is for the case where it's considering one-to-one correspondences between natural numbers and the real numbers. Okay. So this just goes by the nested subinterval property. So you choose a sequence of real numbers which satisfies the following sequence. So I say I take C0 as a closed interval which leaves out A0, and then I choose another interval C1 which is a subinterval of C0 which leaves out A1. And you keep on doing this, eventually you will end up with an element which leaves out all these which you have in the sequence. Okay. And this, unlike the diagonalization proof that Cantor gave later on, this depends on the axioms of the real numbers. Okay. So, all right. So that brings me to almost the end of the talk, what I wanted to tell you about. So this is the idea. So you have proofs, and you look at what kind of elements go into those proofs, and then see whether you can limit yourself to formalisms which don't allow you those constructs, and still can you build up those proofs. And then I showed you 4 lines of development in 4 different cases. And this is the summary of my talk. So, I mean, fundamental theorems are fascinating on their own right, but equally there is fascinating work to be explored when you try to reconstruct their proofs using a minimal repertoire of basic constructs and reasoning mechanisms. Okay? And this is one path that I am trying to do, and I am concentrating on Gödel's first incompleteness theorem with its relation with the Quine's paradox. So in the next few days that I am here at the Newton Institute, this is what I will be trying to see. So, and just some acknowledgements. There are a number of people who have helped me with this work in the preliminary part of it, and thanks to the organizers of the SAS program for this invitation here. Thank you. So if there are any criticism, comments, I am happy to hear it.
So diagonalization is a basic tool in complexity for proving that time hierarchy theorems, for example. Is there any sense you can ask? Can you ask the question? Can you avoid diagonalization in this complexity theoretic results? Is there anything reasonable that one can say?
Sure, that's another direction in which I can extend this, but I have not looked at complexity results yet. Yeah? I'm just focusing on the basic theorems. Yeah? So when, for example, if you, there is already some work in complexity, in barriers and complexity theory, which goes in this direction. But it's in some way it's kind of dual. There they say, if I use diagonalization, in spite of having diagonalization, what is it that I cannot prove? Okay. Now I'm trying to do some kind of the opposite of that. I say that you don't have diagonalization, can you still prove this? Okay. So in that way it's different, but nevertheless, the same philosophy, the same idea can be extended over to the complexity results, definitely. Surely, in a meaningful. Yes.
Your example of Cantor's theorem without diagonalization.
Yes.
I don't know. It looked to me it was kind of cheating. Weren't you using, I don't know, somehow the properties of real numbers that we know of this close integral?
Yeah, sure. That example comes from Cantor himself. Yeah. But that was the very first proof. I showed it to you because surprisingly that's not very well known. He had that proof even before he had the diagonalization proof.
Yeah,
but it does make use of the axioms of real numbers, so it's specific to that setting. Okay, you cannot just take set theory and then say this proof will work. I also need, this is just when you're trying to show for the case where I have natural numbers and the real numbers, not any set and its power set. Yes. Yes, please.
So there is some work in the constructive mathematics, computational setting, where people do explicitly try to set up their system to avoid them.
Yes.
How does your work relate to that line?
So I don't know of any formal connections between that. So you are right in that. Constructive mathematics. So in the case that you take a particular framework, you take a particular axiomatic setting, and so that kind of limits what is the things that you have at your disposal, and then you try to develop this subject on your own. Yeah. So this is very similar in spirit to that, very much. Okay. But I'm trying to do this in standard classical mathematics. I'm not taking intuitionistic mathematics or intuitionistic logic. You know, but it is related to that. Yes.